this is Becca with Empowering Pumps and Equipment. I'm very excited to have Tony Furst with Takeo here today. Tony, why don't you introduce yourself?
Hi, Becca. So, as Becca said, I'm Tony Furst. I'm a um, senior systems engineer in the commercial training group with Takeo. I've been in the HVAC and plumbing industry for almost 50 years now, if you can believe it. Um, I started out working for my father. I actually grew up in this industry. My father was a mechanical contractor, so I grew up in this industry. Um, I got out of college and went to work for a small little air conditioning company in La Crosse, Wisconsin called Train. And I was a failure analytics engineer for Train. Basically, I got to destroy stuff for a living and figure out how we broke it and what we could do to make it better. So I did that for almost 30 years. Left there, went to work for a consulting engineering firm, was head of forensic engineering for a consulting firm, did a lot of design work and high-end design work on a lot of big central energy plants. Then left there, went to work for another pump company, was there for a number of years, and then came over to Takeo last year.
Well, I'm sure Takeo is glad to have you, and that's quite the resume. So I'm excited to be able to learn from you today.
Cool.
Well, we're going to talk about sizing and selecting booster pumps, and I'm going to let you go ahead and take it away, and then we'll come back and do some questions.
Okay. So one of the things that we look at in a building is we look at the plumbing system and we look at domestic water distribution. And depending on the building type, we may have, a lot of times we have a booster pump on the plumbing system to distribute the domestic water throughout the building. The problem is, we think about it in our house, and in our house, we rely on street pressure. And there's enough pressure in the city main to get water into our house, typically 2 or 3 story house, with no problem at all. The problem is when we move into commercial buildings, between the volume of water that we need, as well as to overcome the height of the building, to make sure we have adequate water pressure at the top floor of the building, we have to put a booster pump in. And so that's what we really want to talk about, is where you use booster pumps, where they belong in a building, and kind of how you size and select them, and what's important to think about when you size and select these booster pumps. So let's kind of talk a little bit about why we need booster pumps, kind of the simple stuff. Let's start there. So if I have variable or inadequate street pressure, so there are parts of the country where the city street pressure is only 30 or 40 pounds. Well, if I have 30 or 40 pounds, I'm not going to be able to get water pressure to the top of a building. If it's a 10-story building, I'm not going to get water to the top of that building and be able to have 35 pounds at the top of the building. So I need to put a booster pump in to increase that pressure up to what I need at the top of the building. So the other thing that falls into this category is my building demand. Maybe I've got enough adequate pressure and volume for a very low demand, but what happens under high demand conditions? Is it an apartment building? Is it a condo? What does the building demand look like from 6 o'clock in the morning to 6 o'clock in the evening? What are the changes that are happening to the building demand over the day and even into the night if it's a residential building? We also have, depending on the part of the country we're in, we have break tanks. And a break tank is nothing more. The city water comes into the building, goes into a tank, kind of like a cistern used to be when we had cisterns on farms and people's houses. And that break tank holds the water, and then we pump out of the break tank out to the building. And what the break tank actually does is keeps the building water system and the city water system. That break tank provides a break between the two systems, so they're not ever directly connected to one another. And that's real common. There's a lot of them in New York City, Chicago, down in Texas. There's a lot of major municipalities that require break tanks between the city distribution system and the building's plumbing distribution system. The other thing we have to think about is industrial process. And what do we do in an industrial process environment? So let's say it's a manufacturing plant and they use domestic water for parts cleaning. or in a food processing facility, they need higher pressure to do washdown. In animal processing facilities, things like that. So they may not have adequate pressure, and they need a higher pressure for whatever processes are going on inside the building. So you'd put a booster pump in to take care of that. And then there's always irrigation. So y'all all know what a golf course is. Well, having a booster pump is how they may supply water to the irrigation system to keep the golf course looking good. So there's different places that we put booster pumps in buildings and in different applications. And all of it falls into this same category of domestic water booster pumps. So the challenge becomes, how do we decide what flow rate we need in a building? Well, between ASPE, which is the American Society of Plumbing Engineers, and ASHRAE, we have fixture units. Basically, we look at all of the different types of plumbing fixtures that are in a building, between water closets and urinals and lavatories and bathtubs and shower heads and all these different things that are in a building. You think about it, there's all kinds of things within a building that water touches that we use and you don't really think about, but they all use different amounts of water. And so if I look at a water closet, and most of the time in a commercial building, that water closet has a flush valve on it. Okay. And that flush valve carries a weight of 10 fixture units. And it's a way that we can take the number of devices in a building, assign a weight to them, and then take that value, on which we know all the fixture units that are in a building, depending on whether it's flush valves or tank type toilets. Is it a private lavatory? Is it a public lavatory? Do we do it based on bathroom groups, which is typically what we do in houses, is we do bathroom groups, kitchens, all these different things. We add up all the fixture units in a building. And once we take and know the fixture units, then we can use Hunter's curve to determine how many gallons per minute we need to supply to the building. So Hunter's curve was developed in 1940 by Dr. Roy Hunter. And Dr. Hunter basically created this statistical probability model for plumbing systems. And it looks at the number of fixtures in a building, number of fixture units, and assigned a probability and a flow rate to each of those fixtures. And so we've used Hunter's curve to design plumbing distribution systems since 1940. It's part of the plumbing code. It's enlisted in every model plumbing code. It's in ASPE, it's in ASHRAE, and we've used it reliably for years and years and years. There's a problem with it though. And so when I look at this, and I look at Hunter's curve today, Hunter's curve gets blamed for being overly conservative. Why is that? Well, fixture flow rates have changed and fixture probabilities have changed. So if I look at a high-rise apartment building and I think about what life was like in the 1940s and the 1950s, I look at that and I understand that women didn't work out of the home in the 40s and 50s. They were stay-at-home moms. And kids went to school, they came home, everybody was in the house. And it was only dad that was gone during the day. So water usage was different in the 40s and 50s and even into the 60s. We really didn't see a dramatic shift in building occupancy and building usage until into the 60s and 70s. So if we look at what's happened to water usage and what's really changed, so this is a really good chart that kind of shows what's happened. In 1940, Hunter's curve was developed. And in 1940, when Hunter's curve was developed, to give you an idea, a toilet required 6 gallons of water to flush. Well, in the 1980s, we started coming up with low flush toilets that used less water because we started to realize that water is a limited quantity. There's only so much, granted, most of the earth is water, but there's only so much water on the planet. And climate change affects the water, how much fresh water we have versus how much salt water we have. And the water we're using today is the same water that that the planet was using millions of years ago. It follows the water cycle. Water falls out of rain, it goes into the ground, gets used, evaporates, goes back up into the sky. It's just a continual cycle. We remember that we learned that way back in ninth grade earth science. So in the 1980s, it was 5 gallons per flush for a toilet. Well, in 1987, ASHRAE realized that things were changing and that the industry was changing. And at that point, they came up with modified Hunter's curve, which started to adjust the flow rates within Hunter's curve for each fixture type. So you still counted fixtures and established fixture units and all that, but modified Hunter's curve also looked at different building types and realized that hospital usage and an apartment building and an office building all had different demand profiles and different usage profiles. So that's what modified Hunter's curve was about. Well, then in the 1990s, we started to drop even lower on gallons per flush and gallons per minute usage rates. Then the big change happened in 1992, which was EPACT, or the Energy Policy Act, which was all about reducing energy consumption, and water is considered an energy. So the whole idea was, with EPACT, was to start making things more efficient. Well, as that's continued to happen, the flow rates, or the gallons per flush, and the amount of water that comes out of the faucet has reduced. And now, in today's world, I have toilets that take 1.28 gallons per flush as opposed to 5 and 6 gallons per flush. Well, that's a dramatic change in how much water is used in a building. Same thing holds true with shower heads. Shower heads used to be 5 to 7.5 gallons per minute. That's a lot of water coming out of a shower head. Today, you can't find a shower head above 2.5 gallons per minute. So significant reduction in water usages. If you bought a new washer and dryer anytime in the last probably 10 to 15 years, they're all high efficiency machines, which means they use less water to do the same amount of work. So all of these things have reduced water demand. And because of this reduced water demand, we really have to think about how we're sizing and selecting booster pumps and where there are alternative methodologies to sizing our domestic water systems for our buildings. And to that end, my good friends over at IAPMO, which is the International Association of Plumbing and Mechanical Officials, they have created, in concert with a couple of different universities, the water demand calculator. And what the water demand calculator really does is it is a new probability index and flow rate index to take everything that we've learned over the years about Hunter's curve and put it into today's terms, into what's really happening in a building today. Because there's several things that we have to understand with this. When we use Hunter's curve and that determines a flow rate, well, that also determines a pipe size. What we found is, and I'm sure everybody's heard about Legionella. There's a huge case going on in New York right now. They've had 60 some cases of Legionella disease and several deaths already. Now they've linked it back to cooling towers, but we have to understand Legionella occurs naturally in our water distribution system, even in municipal water. What happens is when we oversize the plumbing system, that pipeline is bigger and we don't turn the water over as fast. If I have a 6-inch water main into the building, but I really only need a 3-inch water main. What that means is I don't clear that water main and replace the water in that pipeline as fast as I should. Okay, so that's part of the reason behind the water demand calculator, is really to look at understanding the demand profiles and understanding how they've changed over the years and taking into account new high efficiency fixtures. So if we look at the water demand calculator, depending on the type of building, and right now the water demand calculator is focused on residential structures, but they are working on and should have out very soon a commercial version to allow it to be used for commercial buildings. If I also look at the UPC and the IPC, there are different methodologies in there to size the systems as well, besides the water demand calculator and Hunter's curve. It's really about understanding the building type and the reductions in fixture use. So anyway, it's really still a statistically based method for estimating peak water supply demand. And right now it's focused on single and multifamily residential. It's available for download. If you go to the IAPMO's website, you can download it from the IAPMO website. It's a great tool to play with to get an understanding of the changes within the industry. So what I really want you to see is, if we look at this load profile, this is a load profile for an apartment complex. And if you look, this system was designed for about 350 GPM as the max demand on the system. Well, what we noticed is that at no time did we ever hit what the real design demand was. This building at 7 o'clock in the morning peaked at 225 GPM, even though it was designed for 350. Okay, so we never ever got to what it was designed to do. And if we look at it, most of the time, that system was less than 50% of the maximum capacity. So at very, very small percentage of the time did we ever get to that close to that peak demand. And what this tells us is that we really have to think about the booster pump and how we're selecting that booster pump and how many pumps we really need. And it's understanding the variability in demand from minimum load to maximum load and how best to utilize our pumps. So if we understand the building and we understand all the different things that affect water demand in a building, we've got morning rush, people are getting ready, they're going to work, they're taking showers, they're getting ready to get out of the day. And then water demand drops off because everybody's in the building, everybody's gone, everybody's at work. Well, then we get another peak at lunchtime. People come home for lunch maybe, and so we see a little bit of a peak. And then we see another peak in the evening because people are coming home, making dinner, kids are coming home, all that kind of neat stuff. And then overnight, it drops off to nothing. And you see some changes throughout the year, depending on whether it's summer or winter. There's a lot of people, dead of winter, it's super cold outside. They come home in the evening and they want to take a warm shower because they've been outside shoveling snow or out playing in the snow with the kids, things like that. So we see different changes in demand based on time of year. So let's kind of look at what we do with the water once we send it out of the booster pump and understand what's going on. So we look at a typical distribution system. We're going out of the booster pump and we're going out to the floors of the building and we're feeding all these bathroom groups. Pretty simple stuff. Well, how do we decide what kind of a booster pump we need? Well, first of all, we got to figure out what the system requirements are. And that's really understanding Hunter's curve or the water demand calculator or some methodology to determine what our demand flow needs to be in the building. Then we have to figure out what our suction pressure is, what the pressure coming in from the street is. And that's typically done with a hydrant flow test and figure out, in a hydrant flow test, we really want to know if we're flowing fire hydrants in the case of, there's a fire, what's the city pressure going to drop to in its worst case condition? okay? Because I can't predict when there's going to be a fire. I have no way of knowing. So I've got to calculate my system demand based on that worst case condition. Okay. So now I know what my minimum suction pressure is. Now I've got to figure out, okay, how high do I have to push the water in the building? Is it a 5-story building? Is it a 10-story building? Is it a 50-story building? That tells me what my elevation change is. Then I've got, now that I know flow rate, I can figure out what pipe size I'm going to have, and this determines my friction loss. Friction loss is fairly minimal in a domestic water system. It's not like a chilled water or hot water system, so friction losses are a lot lower. But then I'm going to put safety margin in. And safety margin, as I tell people when I teach design classes, is be very surgical and very mindful on adding safety margin. And understand that adding safety margin on the pressure side is one thing, but don't add safety margin on the demand side, because we know if you're using Hunter's curve, that system's going to be very, very conservative in its water demand requirements. So don't add safety margin on top of an overly conservative design tool. Okay. So now you figure out the total head that the thing is required to have. Now you're going to look at selecting the appropriate booster pump. When you select your booster pump, one thing you really got to understand is that we understand that the demand on the system is going to be lower than what we calculated at. And so traditionally, we've always done booster pumps with duty standby. So we've had two pumps. One's for the load and there's a backup. Well, the problem with that scenario is we end up with one really grossly oversized pump. And we understand that all pumps have a minimum speed, minimum flow. And it's typically 30% of best efficiency point. Well, if I've got two pumps there, each size for 100%, a lot of times that pump's going to want to run way down at the bottom end of its speed curve, which is not good on the pump. What we really want to do is we want more pumps, but smaller. So instead of selecting a booster pump with a duty and a standby pump, I really like having 4 pumps, each size for 25% of the load, so that now I get really good low end turn down. So I can really come down to that minimum flow that I'm going to see in the building. But when I need it, I've got plenty of pump capacity there to handle full load. And in those cases, I actually get much better performance out of my pumps. I have less wear and tear on the pumps. At the end of the day, overall, I'm going to increase the longevity because I'm going to have less downtime and less likelihood of breakdowns. Okay, as well as increased energy efficiency, because I'm going to really capitalize on the affinity laws in reducing the absorbed power per pump. Okay, so when I look at this, the way a booster pump is going to work is, I've got variable speed drives, I've got a pump controller, and then I've got my piping and my package losses, friction loss in the piping system, and all that kind of neat stuff. So what I'm looking at is I'm really concerned with the residual pressure at the highest point in the building, at the most remote fixture. So if you think about it, I've got a booster pump sitting down in the basement. I've got piping that goes out to the building, and I may have multiple risers, but generally, the booster's in one corner of the building, and I'm going to someplace at the opposite corner of the building. So I need to make sure that I have 25 psig in a residual condition, so flowing water at that most remote fixture. And so I've got to select my pump and control my pumps to maintain that 25 psig residual or 35 psig static under all conditions. Okay. And so if I look at an apartment building, and before anybody crucifies me, I know the drawing is wrong. I just haven't fixed it. the backflow and the water meter are in the wrong order. But anyway, so if I look at this, I've got a 100-room apartment complex, and I've got 115 foot of elevation change from the basement up to the top floor of the building. So it's a 10-story building, 10 apartments per floor. I've got a bathroom group and a kitchen sink per apartment. And because I've got flush tanks, I only need 20-pound residual. Okay. So what I'm going to do is I've got a street pressure of 40 psi. I've got 20 pounds of loss between my backflow preventer and my water meter. That's the two things that are critical, even though they're in the wrong order. But I've got 20 pounds of loss. So I've only got 20 pounds available to my booster pump. I have to boost that pressure now enough to get 20 pounds to the top floor of the building. So now I've got to do 43. I've got to do about 100 pounds of boost pressure above the incoming street pressure. Okay. Now there's a little bit more loss in there than just the 20 pounds to the backflow and the water meter because you've got piping losses. But for simplistic sake, we're just going to say that we've got a 20-pound loss. My 40 pounds is right ahead of the backflow preventer, not accounting for street losses. And so in this situation, now I'm going to have my 20 psi at the top of the building. Now, the way booster pumps work is we have two choices. I can either put a pressure transmitter all the way at the top at that most remote location, or I can have software built into the controller that means I can have a pressure transmitter on the booster skid, and it does the calculations and it understands friction loss and understands how it can reset the pressure based on demand at any point in time. And all of us that build booster pumps, we all have our own little ways that we do this, but it's all based on the requirements of ASHRAE 90.1. And ASHRAE 90.1 says that we either have to have a remote pressure transmitter or we have to have software that emulates having that remote transmitter. And so that's what we all do. We have the ability to do either one. We can do the remote or we can do the software. And it really depends on your building type as to which one is the best for your building. More simplistic buildings, software anticipation works really well. If it's a very, very complex building, hospitals are a really good example. Hospitals are fairly complex plumbing systems. I have found that a remote pressure transmitter can work better in a hospital situation because of the variability in how hospitals actually operate. So anyway, with that, we're kind of at the end of the slides, and now we can talk and answer questions.
Awesome. Well, you can go ahead and take your presentation down, and I took lots of notes, so I'm excited to dig into some of these questions. I love your
Cool.
presentation. Thank you so much. So it was very interesting with the flow requirements that you were talking about and the high efficiency fixtures. Like before you kind of got to that, that was a question ruminating for me of, how does that change with knowing that people are making sinks and faucets, the shower heads, like all of that to be more energy efficient. So with knowing the higher efficiency fixtures, which is decreasing the water demand, when you talked about the water demand calculator, like is that really what people are needing to make sure that they look at in addition to the modified Hunter's curve?
Yeah, so it really depends on the building type that you're in. In a residential setting, now it could be a condo, it could be an apartment building. I mean, it doesn't make any difference whether it's a high-rise condo building or an apartment or, a 200-unit, 3-story apartment building. Doesn't make any difference. It's still a residential structure. The water demand calculator works in that scenario really, really well. And IATMO is working. There is a group at University of Cincinnati working very strongly on developing a water demand calculator for commercial applications. The problem with understanding commercial applications is there's a lot of diversity in building type. I mean, if you think about commercial buildings, we have restaurants, they got a fairly high water usage because they're washing dishes, things like that. Then we've got office buildings. Think about your 10 or 15-story office building. How much water do they really use during the day? It's flushing toilets and washing hands. There's people making coffee in the building and things like that, but you don't have people taking showers typically. Okay. Then you got manufacturing. Okay. Well, if I look at the manufacturing environment, depending on the manufacturing facility, they may have, is it a chemical processing facility where they're using a lot of water? Or is it a chemical facility where they require that employees take showers before they go home? There's a couple fertilizer companies that I'm familiar with that their employees are required to take showers before they go home because of the chemicals they're exposed to at work. They don't want them taking that stuff home with them.
Yeah.
And then we look at hospitals. And we have hospitals, we have medical office buildings, we have nursing homes, we have assisted living facilities. All of those type buildings have different water usages. Hospitals are all over the map. Is it how much surgery do they do? I live in Columbus, Ohio, so I'm very familiar with the Ohio State University Medical Center, and their water demand is all over the map because of just the sheer size of the facility. So this is what they're trying to sort out on the commercial water demand calculator as to how to figure out what that probability matrix really and truly is, and knowing that fixture units are going to come down because we're using less water. Even in a commercial building, we're still using high efficiency fixtures. We're using low volume flush toilets. Faucets are still, I've done some hospital design in recent years that a hand washing sink is 0.5 GPM for a hand washing sink. That's not a lot of water. Years ago, I can remember the house that I grew up in, our bathroom sinks were 2-gallon per minute faucets compared to, a half a GPM. Big, huge difference. So same thing's holding true in hospitals.
Yeah. And I think too, I mean, again, I know things continue to evolve. I know that on your timeline that you had, it kind of stopped at 2019. Obviously, there was big changes over COVID, but even now, like I feel like things continue to evolve in terms of working and people being home and then going back to the office and that kind of stuff. So I'm assuming that all of that is being taken into consideration and continuing to monitor so that you can have those accurate levels.
Right. And we've even seen this in current office buildings where the building usage is not what it used to be. There's a lot of companies that they haven't gone back to everybody being in the office. COVID kind of changed our work environment, and there's more of us that work from home. Now, I've always, most of my career, I've been in a position where I'm not in an office, but it's dramatically changed since COVID. That's gotten even more so since COVID.
Mhm. Yeah, and definitely something that you need to have all of the information so that you know that you're picking
Right.
out the right sizes. And then one of the other things that you had mentioned was the hydroflow pressure, so that's city pressure. And I mean, how do people get that information? Is that readily available or how is that process?
So, and let's look at new construction because that's the easiest way. If I'm gonna build a new building and I'm the engineer for that building, I'm going to reach out and I'm going to contact the city, whatever municipality that we're building in, and we're going to schedule a hydrant flow test. Now, it may be the civil engineer that does it. It may be me as the mechanical engineer, but we're going to schedule a hydrant flow test. And basically, you get with the city, the fire department goes out, hooks up to a fire hydrant, and they turn the fire hydrant on and they flow at full flow, whatever that hydrant can do, and it's usually a couple thousand gallons a minute. And they're going to see what the pressure is before they turn the hydrant on, okay, under a zero flow condition, and then they're going to see what the pressure is when they're flowing, and they'll calculate out how much water they're actually moving. And what we're really concerned about is what is left for pressure under that full flow condition. Because I may go up and hook up to the hydrant and test the pressure, and I may have 60 pounds there. But when I turn the hydrant on and I go to flowing 1,000, 1,500 gallons a minute, 2,000 gallons a minute, depending on what that hydrant is rated for, I may drop down to 10 or 15 pounds residual as what's left. Okay. So when I design my booster pump, I have to design assuming that, let's say it's 15 pounds, that's the pressure that I got available all the time. Because I can't predict when there's going to be a fire at the building across the street. Mm-hmm. You know, there's things I can't plan for. We know they're going to happen. We just don't know when. That's the problem. What we have to understand is, though, when I size the booster pump for that low pressure condition, i.e. in the event of a fire, most of the time my incoming pressure is higher than that, which means the booster pump has to do less work. Okay, I don't have to boost the pressure as much. And in that case, that's where, I talked about using more but smaller pumps. That's where more but smaller pumps really comes into play, because most of the time I'm going to have the higher pressure available because I don't have a fire across the street all the time. Mm-hmm. So that's where more and smaller pumps really comes into play as well.
Okay. And I mean, I had a question about that, so I feel like you just led it perfectly into that. I mean, I definitely am sure in the grand scheme of, you know, not having less downtime and not having to do as much maintenance on them, but what does that financial impact when it comes to buying more pumps at that smaller range than, say, so four smaller one versus two bigger ones? I'm sure that that's probably something that customers are curious about in terms of, you want me to buy four pumps instead of two?
Yeah, it is a concern, and I've had this discussion with owners on a fairly regular basis. So yes, you're going to pay a little bit more upfront. Now it's not like it's 100% more going to four smaller pumps versus two big pumps. It's probably on the order of 20-25% premium to go to more but smaller pumps. What you have to understand is, though, that probably over the first 3 to 5 years of ownership, you're going to pay that back in energy savings. Okay, because you're running smaller pumps, and we know that pumps follow the affinity laws. And so if I look at this and I'm running at a reduced flow rate, my horsepower on a VFD moves up and down by the cube. Okay, so if, let's say it's regardless of what the pump is, if I reduce the speed by 10%, that is a 27% reduction in actual absorbed power out of that motor. Okay, so a roughly 20% speed reduction results in a 49% reduction in absorbed power. Okay, so by having more but smaller pumps, I get even greater energy savings because I can turn that pump down even lower to meet those low flow conditions that we have.
Okay, so yeah, so it's you really need to look at the big picture and well into the future, and you're going to get that ROI back.
Right.
It's just looking at it more holistically than the
The,
right here and
the
there.
challenge, right. The challenge with most owners is most owners look at first cost because nobody takes the time to explain to them life cycle costing. Mm-hmm. And if you really look at it and understand life cycle costing, then you're much better off. You know, um, as engineers, design engineers, we design to code, because there's building code that we all have to design to. The problem is we have to understand code is the absolute minimum that we have to do. Okay. Code is not that code is bad. I don't want anybody to think that I'm saying code is bad, but code is the absolute minimum we have to do for a building. Well, why do I want the minimum? I mean, think about it. Okay, way back when I was in school anyway, D was a passing grade. I think it still is today. Um, so think of code as the minimum passing grade. Okay, I know my father would have kicked my butt if I'd have gotten D's to just get by. Okay, so why do we want to just design to code minimum? Why don't we design better than code? Why don't we explain this to the people that have hired us? I mean, building owners hire engineers because they want they want smart people designing their buildings. So why wouldn't we have that conversation with that perspective, with that owner about, okay, what is important to you? Is energy efficiency, water efficiency, all these things, are they really important? Do you want me to just design code minimum? Or do you really want a building that's going to give you better energy performance? Because you're going to pay that energy bill every month from now until they bulldoze that building into the ground. And this is what people don't think about.
Yeah, that they should.
Yep.
What would you say are the most common mistakes that you see when it comes to sizing and how people can, I guess, just putting name to it so that they can hopefully avoid it?
Well, we know that Hunter's curve will lead to a very conservative design, that you will have lots more capacity than you really need. And then engineers, in an attempt to make sure they never get sued, they add safety factor on top of whatever they come up with. So let's say they count fixture units and they go, okay, and my count says that I've got 200 fixture units. And that equates to, and I don't know what it is because I'm not looking at Hunter's curve right now. Let's say that's 250 GPM. Okay. Well, instead of designing it for 250 GPM, I'm going to want my booster pump to do 350 GPM. I'm going to add another 100 in there just because, just in case. The reality is just in case needs to be fired. Because I put this safety margin in there and I already know that my model is extremely conservative because it was built in the 1940s. And today it's, 2025. Fixture units have changed. The demand has changed. So be careful how you put safety factor in. Now, yeah, if I look at it and go, okay, I need X number of PSI, X number of pounds of pressure to meet the system demand. Okay, maybe I want to put a little more there to cover piping changes, things like that, to cover piping age, because we know as piping gets older, we get scale buildup on the inside of the piping, pressure loss is going to increase. So having extra reserve on the pressure side is not so bad. On the flow side, it's a whole nother issue. So it's understanding where to put that safety factor and where it makes sense. It's not paying attention to what your building demand really is and understanding load diversity within a building, because every building has a diversity profile. Depending on the type of the building. Is it an office building? Is it a hospital? Is it a hotel? All of them have different demand profiles. And you really have to understand that and understand the diversity that's going to occur in that building.
All very good tips. What about retrofits and the opportunities that are for existing buildings? Can you kind of talk on that a little bit?
Sure. So the way we used to do this, kind of the way we were moment here, is we used to have constant speed booster pumps that the pump ran at the same speed all the time, and it had a constant pressure valve on the discharge side that basically added pressure loss to the system to reduce the pressure going out to the building. And that design worked for a number of years. And with the advent of VFDs have gotten significantly more reliable. They've gotten smaller. They've gotten more cost effective. So we put VFDs on everything. When we look at a booster pump, what I have to look at is, one, I don't want, I'm not going to put constant speed back in. I'm going to go with a variable speed booster pump. I've got to look at what the water demand really and truly is. Because if I just go back in and look at the tag and it says, 500 GPM at X PSI boost, yeah, I can put that back in, but it's not going to be the most efficient. So what I want to look at is, one, going to more but smaller pumps on a skid. Two, I want to look at and measure the actual water flow. So I'm going to put what I typically use is an ultrasonic flow meter. So it straps onto the outside of the pipe, and I measure the water flow for a week and see what the demand is and watch what those peaks and valleys are over an entire week's long period. Then I can take that data and say, okay, Mr. Owner, your booster pump originally was sized for 500 GPM, but under all these different conditions that happen over a period of a week, you never got above 250 GPM. That was the most you ever used in any single point in time over the past week. If I size your booster pump and downsize it to meet what you're actually using in the building, here's what the cost savings are going to be. And look at, motor horsepower savings, multiple pumps in parallel, what I'm going to save in horsepower, what I'm going to save in energy. And I can do all those calculations and figure out how much I'm going to save. That oftentimes will easily pay for the retrofit once you understand what the savings are. And that's the best thing to do, is to use an actual ultrasonic flow meter and figure out what the real demand really and truly is.
Yeah, and then it's not just a guess too, or even if it's an educated guess, it's you have the real data of what you're using, and then you can uh pick the equipment accordingly to what you actually
Exactly.
need.
Exactly. Because then you're making intelligent, informed decisions.
Mhm.
Now, maybe the building owner is going to look at it and say, no, I don't want to do that. I want the same flow. But you've given him all the data, and you've helped him at least understand what his building is doing. Now, maybe he knows something that's coming. Maybe he's got a new tenant coming in that's going to use more water that you don't know about. But at least he has an understanding of what it's doing at that moment in time. And then he can make the decision to do something different.
Yeah, absolutely. So I really like that you kind of talked about what we did in the past and what we're doing now. Can you talk about where you think we're going when it comes to booster pumps?
Yes. So what's ultimately happening is we know that water age is a significant concern within a building because we've oversized plumbing systems for so long. And we know that Legionella naturally occurs in municipal water systems. It's in every water source out there. And even though we treat the water at the municipal plant, we kill it, we kill the bacteria by chlorinating and other things, it regrows in the plumbing system. And the longer that water sits in a municipal water system, the greater the chance is for bugs to grow in the water system. I know this is the one thing that people hate to hear, but it's the reality. So what's happening is there is a significant change in our industry driving system designs to minimize water age. Okay. So if I look at most municipal systems, they chlorinate the system. That chlorine only lasts about 5 to 7 days. Well, how long does it take to get from municipal water treatment plant to your house? Depends on how big the water main is. I live in a rural area, and from where the water plant is to where my house is, it's probably 40 miles, 50 miles. Okay. I know that by the time the water gets to my house, the chlorine residual is very low. I know that. I've tested it. So I know what it is. Buildings that are closer to the water treatment plant, their chlorine residual is going to be a little bit better. But I know that because of things that we are doing in the industry, we're doing things to reduce water age. So we're making pipelines smaller. We're right sizing. This is the whole idea behind the water demand calculator, to really right size water services coming into a building, to right size the distribution piping so that we minimize the risk for waterborne bacteria like Legionella. And there's a whole litany of other ones that go into that. Legionella just happens to be the one that's most prominent that everybody hears about. So as we drive to lower demand, what we're going to see in the booster pump market is smaller and smaller booster pumps. Okay. So right now, there's a lot of times we have booster pump size for 300, 400, 500 gallon a minute. Well, as we start to downsize and minimize the water age, the services are going to get smaller. Those booster pumps now, we're going to start seeing more and more booster skids that are 100 gallons a minute, that are 50 gallons a minute, that are more appropriately sized based on what the water usage really and truly is, as we get better at the demand calculator, like the water demand calculator, or the 21st century version of Hunter's curve.
Yeah, which is going to continue to help with our efficiency and our energy usage too.
Exactly.
Awesome. Well, that's all the questions that I had, but I wanted to just
Awesome.
open it up of, is there any last words that you would like to leave everybody with?
Pay attention to your design. Think about what you're doing. Think about what is important, and don't be afraid to have open and honest conversations with the person you're working for. Ultimately, we as engineers are working for a building owner. That building owner is not an engineer. He's a building owner. He's a real estate developer. He's whatever, administrator of a hospital. They're not experienced in what we do. That's why they hired us. Don't be afraid to have those conversations with them and find out what's really and truly important to them, and help to counsel them on what decisions to make. And don't be afraid to have those conversations.
I love that. Communication is key.
Yes.
All right, Tony. Well, I really appreciate you talking with us and sharing your expertise and knowledge. I really appreciate it, and I'm looking forward to learning more from you in the future.
Cool. Look forward to it. As always, it's been fun.